The first one we're going to talk about is whether or not things are linear or non-linear. What word do you hear embedded in linear? Line. So we're trying to decide if we've got things that are going to be lines. So how do we know if we have a line? So the equations for lines look something like this, or something like this, or maybe even something like this. In all of these examples that I've written, do you notice how x is being raised to the first power? If there's no exponent given, that means there's a little baby 1 hiding there. So all of these are being raised to the first power. So it has to have not raised to a power other than 1. So basically it means raised to the first power, if we say that better. Raised to the first power every single time. So in order to be linear, we have to be raised to the first power. Any other power? Nope. When you look at the graph of something that's linear, it should be a straight line. Sometimes it'll have a slope to it where it increases from left to right or decreases. Other times it could even be horizontal or vertical. But again, it should be a straight line. So what it is, here are some examples of what it is. Those are some equations that we could use. Again, it's anything where x is being raised to the first power. It's anything where we have a nice straight line that you could like put a ruler up against and you could see that it matches. Okay, so let's look at the flip side. So we've got linear. Well, what is nonlinear? So this would be not a line. These are graphs where points will not lie on the same line. So it could be something that looks like this. What do we call that U-shaped graph? Parabola. It could be something like this. It could be something like this. That's what our trig functions look like. Anything that has curvature to it, not linear. Also, it can't be written in this format. Do you remember specifically what this is called when we have y equals mx plus b? Slope-intercept, yep. So this is specifically slope-intercept form. We're going to get back into talking about the different forms of lines. So this one is specifically slope-intercept. So if it can't be manipulated and written in that form, it's also not a line. So let's give some examples of nonlinear things. So y equals x squared, not linear, right? Because it's squared. Y equals x cubed plus 15. Again, not linear because we have x cubed. Let me show you a trickier one. Y equals 5 over x. Do you remember what kind of exponent this has if it's in the denominator? Exponent laws, maybe from even like 2 years ago. So if it's in the denominator, it has a negative exponent, so this is not linear either. So there is kind of an exception to the rule. You can have an instance where it's not linear, but it looks like x is being raised to the first power. It looks like it, right? Because there's a 1 there, but it's actually a negative 1 because it's in the denominator. So this one is not linear either. So this is really, when it's in the denominator, that's really x to the negative 1, so that's why that one's not linear. Ooh, I want to add another thing to this list. So these were the what it's not over here. What about y equals 4? What type of, that's a line. It doesn't have an x in it, but what type of line is that if I say y equals 4? Horizontal, right? It's at 4 all day long for y. What if I said x equals negative 3? Vertical. So we're looking for x to have an exponent of 1, or we can have one of those more simplistic cases where we have x equals 5. y equals 7. These are also linear. These are just your horizontal and vertical examples, like the ones I drew over here. Okay, so I want to add those too, because those are all, so this is what it's not, are these. All of these are examples of things that are, yes, linear. So all these things are linear examples. They all go together. All right, let's look at some examples. What does the word justify mean? Prove. Explain. So we've got to justify our answer. So we've got to give a little tidbit of like, okay, we said this is the answer, but why? Why? Look at number 1. Now, notice where your x is. Is the x in the denominator? No, it's off to the side, right? So we've got 0.5x would be another way to write this. So this is 1/2 x, or we could think of it even as 0.5x. Linear or not? Linear. So linear, and I'm going to say because, you guys know the shorthand for because? B/C means because. You can write out the whole word if you really want to, or you can write that if you'd like. Because x is raised to the first power. And again, you don't have to use the exact same words I do. So if your wording doesn't match up to be identical as mine, but it makes sense and it explains your answer, that's all I'm looking for. It doesn't, like I said, I'm not looking for you to use the exact same words I use. Linear or not for 2? Yes or no? No. Non-linear. Why?
X isn't raised to the first power.
Because x is squared. Or you could say raised to the second power. But again, make sure you actually do justify your answer. I know sometimes on homework we get a little lazy and we're like, here's the answer. I don't want to tell you why. It's just homework. But it's good to get in that habit, because on a test or a quiz, if you don't justify your answer, that's half the points, right? So if I were giving this question on a test or a quiz, you get a point for telling me linear or non, and then you get a point for the justification. So make sure you're practicing good habits on the homework, because then they'll carry over. Let's look at this one. Number 3, linear or non? Linear. Again, when there's no exponent there, there's a little baby 1 hiding. So we can say linear because x is raised to the first power. And again, if you have a different way of writing that, and you've written it in your own words, I'm fine with that. It doesn't have to be identical to what I said. How about 4? What do we think? Yeah. Yep, it's being raised to the first power. So yep, it's linear again. Same reason as all the rest. Because x is raised to the first power. I'm sure you guys will think of a good way to get around writing out all those words. I know you guys are good at the shorthand stuff, so if you've got another way of writing it, that's fine, as long as I can tell what you mean. Go ahead and flip when you're ready. Make sure everybody's got that. Okay. These don't say justify, and these are even a little bit easier. They say linear or non. How about 5? Linear. How about 6? Non-linear. It's got some curvature to it. How about 7? Non-linear. How about 8? Linear. Okay, so some of them are just that easy. And remember, when we're in some of these like introductory chapters, we're learning a lot of vocab and kind of remembering some of the things that maybe we didn't remember from years past. Lots of vocab embedded in these years. Okay. Intercepts. Do you remember what I'm talking about if I say intercept? What's an x-intercept?
Where it like hits the line.
Yes. Specifically which line?
The x one.
Yeah, the x-axis. So, here are our graphs. Let's talk your y value is always 0. At your y-intercept, the x value is always 0. So if we were to look at a graph, so I'm just making one up. This would be my x-intercept, and it would be located at -2, 0. So the y value is 0. My y-intercept, bless you, would be located at 0, 3. So this would be my x-intercept, and then this would be my y-intercept. So again, just an example, you can add if it's helpful to you. Now, when I ask you to write your x and y-intercept, you can write it as a point like this, or you can just tell me the number. So I'm actually okay with either way. I'm going to pull out a second color again, kind of like I was doing with domain and range, so I can make sure I show you x-intercept versus y-intercept. So let's take a look at the graphs. Some of them are actually this easy that it's going to give you the picture and say, find it for me. So this is kind of nice. So remember, I'm going to go x-intercept as magenta. So where does my x-intercept happen for number 11? X-intercept happens at 12. And you can write 12, or you can write the ordered pair, which is 12, 0. I don't care which. How about my y-intercept? Where does that live? -12. So my y-intercept is at -12. You do need to label them. So if you did this problem and you just wrote 12 and -12, I don't know which is which. So you need to tell me x-intercept is this, y-intercept is this. Okay? It doesn't matter which way you give it to me, a number or a point, but you need to tell me and label it. Oh, I didn't write INC. Put a T there. Alright, let's look at 12. What's my x-intercept for 12? X-intercept, where does it touch the x-axis? Oh yeah, it doesn't look like it's right on -1, does it? Let's go with -3/4. I promise I will give you good ones on testing quizzes where you're not going to have to guess. And as long as you were close, I would be fine with it anyway. Okay. Y-intercept, so where it touches the y-axis. What does that look like if you approximate it? Yeah, that's what I would say too. Or 3/2, right? You say 3/2. And is it positive or negative? Negative, so we need negative. Okay, no, let's see that. Okay, again, you can give the ordered pair or just where it's located, but again, you do have to label it so I know what you're talking about. Let's look at 13. What do we think about 13? What's my x-intercept? 0. What's my y-intercept? 0. So sometimes they'll match, and if they are a match, it's because they live at this point. Do you remember the fancy name for this point? The origin. So we call that the origin. This point in the center right here that is 0, 0. We call that the origin. So again, just some vocab to remind you in case you don't remember what it was. X-intercepts. This one has more than one. That can happen. It can also happen that there are no x-intercepts or no y-intercepts. So we can come across different situations out there. Alright, x-intercepts. There are 2. What would you say they are approximately? 1 and 3. Careful. -1, -3, right? So we're counting by 2s. If I ever don't give you a scale, like you see number 13 has no scale on it, assume you're counting by 1s unless I tell you otherwise. So this one's counting by 2s, so when I look at about where it touches -1 and -3. Okay, let's go to our y-intercept. What do we think? What's that one approximately? Yeah, I'd say 2 as well. But you guys have better eyes than I do. I'm like, you tell me if you think I'm wrong. I believe you. Okay, flip the page when you're ready. So those are just that easy. Looking at the graph, telling me what they are. Alright, let's look at some examples where we're thinking like a real life situation. A little zoomed in for my lighting people out there. Okay. X-intercepts and Y-intercepts. This time we have a chart. So we have Juan, and Juan got a gift card for his birthday. And there was $50 on it originally. And he used the gift card to pay a weekly subscription for a video game. So he paid $10 every week. You can see the amount decreasing over here. What is your x-intercept for this situation? What is it? 5, 0, right? So remember our definition for the x-intercept is that it's when y equals 0. So think about your table. Here's my x, here's my y. Remember, independent is time, dependent is my other variable. So I'm thinking, okay, for my x-intercept, it's when y equals 0. So this would be my x-intercept. So based off of that, what would my y-intercept be? If I wrote it as a point, what would I write? 50 and 0, 50 if I wrote it as a point. Again, you could just write 50, then that's okay. You could just write 5, and that's okay. So let's think a little bit more in depth about what they mean. So here's my x-intercept. What information is that giving me? So what is this 0 representing? What's the 0 telling me? Yeah?
How long it took me to spend the money?
Yeah, so I'm looking at it and I'm seeing it took 5 weeks to get down to $0. So my x-intercept shows me time to get to $0. And again, there's not a perfect way to write that. You can write it in your own words as well. Number of weeks until the gift card ran out. That's another way of saying it. Again, there are different ways. It doesn't mean they're wrong. It's just a different way than I said it. What does your y-intercept show you in this case? The beginning funds. So I'm going to say the amount you started with. And again, you could write beginning funds, and that works as well. Okay. Try 16 on your own. You've got a rocket launch. I'm picturing like one of those like soda bottles where it like psh. Okay, same thing, but you're answering this one. I'm going to freeze my screen because I'm going to do the problem too, and we'll talk about it in just a second. Make sure we match. you my answers. Let's see if we match. You ready? So again, the time is going to be x, you're independent, the height is going to be y. So what this is telling me is if it's at 24 feet, it means it's 24 feet up in the air when the rocket launched. So I guess I'm not thinking of a pop bottle because I don't know why I would raise that to a height of 24 feet. Maybe I let it go off the roof. I don't know. So at time 0, it was at 24 feet. So it was 24 feet up in the air when I let it launch. And then it took, in seconds, it took 6 seconds for it to come back and hit the actual ground. Did we get the same x and y intercepts? And then I tried to explain it again in my own words. So the x-intercept is how long it took to hit the ground. I said landed, you could have said hit the ground. And then the y-intercept would be the height at time 0, or the height when you started, the height where you began. Again, there are different ways to say it. Okay, let's talk symmetry next. Do we feel good about intercepts? Yes? No? Okay, let's talk about symmetry next. One of my weirdest days as a parent, so my son, who's now in 8th grade, which is insane to me, he came home from preschool and we were like, hey buddy, what'd you learn about today? And he goes, cemeteries. And I was like, oh, yeah, it's dark for preschool. And so my husband, who's more chill than I am, because I'm over here like, what? My husband, who's more chill than I am, thinks about just like asking some more questions. And he's like, what'd you learn about cemeteries, buddy? And he's like, it's when you cut something in half and it looks the same on both sides. We learned about symmetry, not cemeteries. Good news. So that made me feel a little bit better because I was like, man, that's dark for preschool people. Anyway, so symmetry is when you cut something in half and it looks the same on either side. Now there are different types of symmetry. There is line symmetry, so we have line symmetry for the most part, right? Like give or take a couple moles, I should look the same on both sides. And then point symmetry is a little different. So line symmetry is a graph has line symmetry. It can be, I don't even know what word they're looking for here. I'm going to say cut by, and I'm going to cross out the word in. I'm not really sure what word they were looking for. It's like Mad Libs over here. I'll put folded. Folded. There you go. Folded in a vertical. There you go. I couldn't figure it out first hour, so I just crossed out the in and made up my own thing. So it's a graph that can be cut by a vertical line so that each side looks exactly the same. So look down at example number 7. This has line symmetry. So this one has line symmetry. Do you see how if we cut it in half, it looks the same on both sides, yes? And another way to think about it is exactly what Sam said, that if you folded it along that line of symmetry, that it would flop over right on top of itself. Point symmetry is when you have a point and your figure is rotated around that point. So you almost have to use your imagination a little bit on this one. This one has point symmetry down here. Specifically, its point symmetry is at the origin. So take a look at this arm of the graph. Okay, so I'm thinking about my graph having 2 arms. Here's one of them. If I take this arm and I rotate it 180 degrees, is it going to land right on top of itself? That's rotational symmetry. So here we're thinking fold and it'll land on top of itself. Here we're thinking rotate, 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 and it'll land on top of itself. Okay, or pivot, whatever word you want to use there. Okay, let's flip. We're getting close to being done, I promise, guys. Lots of little stuff today. All right, last thing, last topic of the day, even and odd functions. So, an even function, let's start there. An even function is when it is symmetric to the y-axis. So it has to be symmetric to the y-axis. Must symmetric to y-axis. So it can't just have symmetry, it has to have symmetry to the y-axis. That's the only spot it can have symmetry in order for it to be even. Another thing that's true about even functions, and I'm going to explain this more in a minute, if you plug in the negative x value, it should be the same as the positive x value. So for example, let's say I counted over to 2. Where's my graph at 2? What point would that be? What's my y value there? 0, right? I'm not getting answers to make me nervous. Do you agree that f at 2 would be 0, and that's 0 in terms of y? What if I found f at negative 2? What is f at negative 2? 0. And so in this case, my x was 2. So again, what we're saying here is that if you look on one side, you should get the same y value as you should on the other side at that exact same time. All right, in terms of point symmetry. So if we have point symmetry, what you're going to find is you're going to have an ordered pair. So let's say we have an ordered pair at 1, 3. I should also have a point then at -1, -3. So what this is saying is if I look at any spot, they should be opposites of each other if I look at that same affiliated location on the other side. So you should end up where you have ordered pairs where they are the opposite of each other. So if this is 1, 3, we switch both the signs. Or if this was my original point, I switched both the signs to get here. Okay, let's look at some examples and then we're done for today. Determine whether each function is even, odd, or neither. They gave me both the equation and the graph. Let's look at the graph first. Based on the graph, isn't it kind of a little hard to tell? Doesn't it look like it's almost cheated over to the right a little? Do you agree? Okay, so I'm going to show you a way to double check it. So for me, when I look at 19, I don't know why it's 19, but 19, when I look at it, it looks like cheated to the right. So what I'm going to do is I'm going to double check using this piece of information. So f of x equals this. I'm going to figure out if f of negative x equals the same thing. If it does, then it's even. Again, I can't tell by the picture because it looks a little funny. So what I'm going to do is I'm going to replace my x with a negative x. So all I did is I picked out my x, and in place I put a negative x. Whenever you insert something in, you want to put it in parentheses. Alright, let's figure out what this equals. If I square something negative, how does it come out? Positive. So this is going to come out 3x squared plus 5. Is f of x equal to f of negative x? Yeah. So this would be even. So again, if you can't tell by looking at the graph, you can plug in a negative and see like, ooh, does it actually work? The next one I think I can tell. What do we think about the next one? Even or odd? Odd. It's got the point symmetry about the origin, so that one's odd. You could pick a point like we did up here and make sure they were the opposite of each other. So let me show you an example of something that is neither, because we didn't see that. Hold on, I had one last hour. My pictures never turn out super well, so I'd rather just steal one that I know works. Alright, take a look at these bottom graphs down here. Tell me which of these are neither. There should be, maybe just one. Yep, there's only one neither. Which one is it? What do you think, Alyssa? 9. I I agree with 9. Do you see why? If you look at 9, is this cut it directly in half? It wouldn't flop over onto itself, right? And if I took this and rotated it about this point, it's not going to land on itself. Even if I tried to rotate it this way, it's still not going to land on top of itself. So this one for number 9 would be neither. We could also pick a point. So if I pick this point, this would be maybe 1/2, comma 2. Do I have a point down here at -1/2, -2? -1/2, -2 would be about here. Is that point on the graph? No. So that'd be another way to check. So there are different ways you can kind of check yourself and see. How do we feel? Okay? Lots of little itty bitty bits of information. Alright, so we have homework tonight. I'm going to tell you what it is. You've got about 6 minutes. I feel like 5 minutes is like my cutoff, whether or not I'm like, start doing homework. So 6 is kind of no man's land. If you are at a place where you're like, oh, shoot, well, I just listened for 31 minutes and 41 seconds and I need a break, I need a phone moment,